Okay, question 7. Consider the following claim. The difference between two consecutive positive cube numbers is always prime. Okay, so, that statement, so you might want to check if the statement is true or not first, to get a rough idea of what's happening. So, 2 cubed minus 1 cubed, that's like 8 minus 1, which is 7, so, okay, sounds sensible. And then you have like 27 minus 8, which is 19, and then, so it sounds sensible, okay, so maybe it works. So let's have a look at a proof. All right, so this is a classic proof question, TMUA, right, when you have to see if there are false claims in the proof. Okay, so line 1, x plus 1 all cubed equals to that. Okay, binomial expansion, I don't disagree with that. Okay, how about option 2? Taking x to be a positive integer, the difference between two consecutive cube numbers can be expressed as that minus x cubed equals 3x squared plus 3x plus 1. Okay, so it's just purely algebra, I think, so I think it's acceptable. It is impossible to factorize this into two linear factors with integer coefficients because the discriminant is negative. I think that's also sensible because discriminant is negative, so you have two complex solutions, so of course you can't factorize it into real linear factors, I suppose. So 3 also looks okay. How about 4? Therefore, for each positive integer value of x, the integer cannot be factorized. Okay, that's slightly debatable because, in line 3, what you mean by the discriminant is negative and you can't put it into two linear factors is that, two things don't multiply to 0 in some way, right? You think about the roots of the equation in some way, yeah? But then, I can easily find a counterexample here. For example, 3 5 squared plus 3 times 5 plus 1, right? This is what? This is 91. And people think 91 is prime, but it's not, right? It's 7 times 13. Okay, so it is factorizable, right? So, we've got to be careful here. Yeah, because not being able to split into two linear factors doesn't mean that for a particular value of x, it doesn't factorize, right? If you can split into two linear factors, fine. Then every value of x, it works. Every value of x, you can factorize, yeah? But then, if you can't split into two linear factors, it doesn't mean that all values of x cannot be factorized, yeah? It means that some cannot be factorized. So that's the key thing here. Okay, so line 4 is not quite correct, so therefore line 5 wouldn't really follow. Line 5 is just a conclusion. So therefore the proof is wrong, and the first error occurs on line 4.